Okay, so today we'll finish up last section on 3.1, and we're going to look at a little bit more of the relationship between inverse trig functions and regular trig functions. Okay, and what we're going to do is look at 6 different formulas. Okay, there's going to be 2 for sine, 2 for cosine, and 2 for tangent. Okay. And what we're basically looking at is when does inverse sine and regular sine cancel each other out? Right? So in this formula, and I'll try typing this in on the calculator. If I type in the inverse sine of the sine of, and then I put a number here, what's basically going to happen is these are going to cancel each other out. And the answer that I'm going to get when I type in what's on the left is whatever is right there. Okay, so inverse sine and regular sine cancel each other out. And the answer you get is whatever you type in. But it only works if you type in a number between negative 90 and 90. Okay? Or if you're doing it in radians, negative pi over 2 to pi over 2. Okay, and let me show you an example, and I'll type in a number that's between what I'm telling you, and then I'll type in one that's not between.
Now, can it be 90 or 90?
Yep, it can equal. Yep. So in this case, it's the less than or equal to. Right. And I'll do it in degrees. Okay. So based on my formula, if I type in the inverse sine of the sine of 15, when I hit enter, what should I get?
15.
Yeah, I'm going to get 15. And I do. Okay, so inverse sine and regular sine cancel each other out. You get back what you started with. Okay, what if I type in negative 70? What should I get when I hit enter there?
Negative 70.
Yep, negative 70. And I do. All right. What's going to happen if I type in inverse sine of sine, let's say, 120. Did I type in a number that's between what I said it had to be between? No, I typed in something bigger. So this time when I hit enter, I don't get 120 back. I get 60. Okay? So that formula only works if you pick a number between negative 90 and 90. Okay, and we'll go through some other examples in a little bit. Okay, like a problem you'd see on the test. But any questions on when this formula works? Okay, so your book calls that formula 2a. What's the difference between formula 2a and 2b? It's a small change, but it's very, very important. Yeah, Amy, you see the difference? Right, we've switched where the sine and the inverse sine are. So now the regular sine is on the outside, inverse is on the inside. Okay, and what will happen is sine and inverse sine will cancel each other out as long as x is between 2 values. Okay, it's not negative 90 to 90. Does anybody remember when I graphed sine and cosine yesterday? What was the highest that sine ever went? 1? And how about the lowest? Negative 1. So this time, this formula only works if you pick a value of x between negative 1 and 1. Okay, and I'll type a few in and try it. Okay, somebody pick a number between negative 1 and 1. 0.5. So when I hit enter, based on my formula, what do you think I'm going to get on the screen? 0.5. And I do. Okay? Any number, that'll work for any number between negative 1 and 1, and you can include negative 1 and 1. How about negative 0.8? What'd you get if I hit enter there? Negative 0.8. Okay, so they cancel each other out. Now, what do you think is going to happen if I type in 1.8? It's not going to work. And this time, I don't even get a different answer back. I get an error saying the calculator can't do what it's asking. Okay? What we're basically asking the calculator to do is take this, and tell me where they cross. Just give it a second, it'll come up. Okay. Do those two curves, those red and the blue, do they ever cross? No. So if you pick a number that's higher than 1 or lower than -1, it's not even possible to solve. Okay, it's just, you get undefined. Right, let's try a few examples. Right, so this is a yes or no, or like a true-false question. Is the inverse sine of the sine of pi over 8 equal to pi over 8? Now, pi over 8 is what units? It's in radians. Now, if you don't want to work within radians, you could always change it to degrees. Okay, so to do that, all we do is take 180, multiply by 180, divide by pi. So the pi's cancel, and you're left with this. Okay, it's 22.5 degrees. Okay, we talked about changing degrees to radians. One of the first things we did. So now we know it's in degrees. Okay. Let's see if we can figure out what formula it's more similar to. Austin, is this one like 2a or 2b?
2a.
Yeah, it's 2a because the inverse is on the outside. What's my restriction on x? What does x have to be between for 2a?
-90 and 90.
And are we between what you just said?
Yeah.
Yes. All right, so this one is true. Yes. Right, so that's all you really have to do. Okay, see which formula it matches up with, and see if your argument is within the numbers it has to be. Okay, next one, same type. Inverse sine is on the outside. Regular sine is on the inside. Okay, does anybody know what 3 pi over 2 is in degrees? Take 3 times 180 and divide by 2. What do you get? 270. All right. So is that one going to work? No. Okay, this is like formula 2a. We have to be between -90 and 90. So the answer here is no. Okay, now we're switching. Okay, now this one is like 2b. Bless you. Okay, regular sine on the outside, inverse on the inside. Okay, when my inverse is on the inside, Emily, what are the two numbers I have to be between? Yeah, -1 and 1. Am I between -1 and 1? No. So this one does not work. That's all you have to write. No. Okay, and the last one is the sine of the inverse sine of 0.6 equal to 0.6. Okay, so same setup as the last one. Inverse is on the inside. So we're still between -1 and 1. How about Sydney? Is that one going to work?
Yes.
Yeah, 0.6 is between -1 and 1. Okay, any question on that? All right, so that's one way you could see these questions worded on the test. Okay, another way you could see it worded is something like this. Instead of the word is, it could say, just move it down a little bit, simplify. If it says simplify, don't write yes. Yes does not tell me anything. Okay, if it says simplify, I'm looking for the number here. So what is the sine of the inverse sine of 0.6? 0.6. Okay, so in the case where it says simplify, I want you to write 0.6. Don't write yes. If it's a true-false kind of question like this, then you can write yes. Okay, so any question on the formulas for sine? Right, let's look at the ones for cosine. Right, so for this one, if we can remember what we learned yesterday about inverse cosine, what was inverse cosine always between? What two angles? Not negative 90 to 90, but 0 to 180. And that's our restriction here. Okay, I'm not going to type this in on the calculator, but if you want to try one, you can. Okay, but in order for this formula to work, your argument, that thing right there, it's got to be between 0 and 180. Okay, and formula 4b just switches around where the regular cosine and the inverse are. And for this one, I want you to think back to the graph of cosine. Does anybody remember what the highest cosine ever went was? Not that high. If you were to draw cosine, what's the highest it ever goes? So this answer is not an angle. This answer is just a number. So think back to that chart. If you look at that chart from yesterday, and you look at the cosine column, what's the biggest number you ever see in that column? 1. And what's the smallest number? Negative 1. Okay, so for formula 4b, you've got to be between 1 and negative 1. If you're not, you're going to get an error. Okay, it won't work. Right, and we won't. We're not going to go through as many examples. We'll just try one of each. Right, so Carter, do you think the cosine of the inverse cosine of 0.95 would equal 0.95? Yes, which formula is that? 4a or 4b?
4b.
Yeah, it's 4b because the inverse is on the inside. And 0.95, just barely, but it's between negative 1 and 1. So that one works fine. Okay, the last one says, is the inverse cosine of the cosine of 210, would that equal 210? No. Why not? What's the highest you can go?
180.
You can only go to 180 because this is formula 4a. This would not work. Okay, so any questions on the formulas for inverse cosine and cosine? Right, and the last two we'll look at are for tangent, and then that'll finish section 3.1. Right, and again, I'm going to try to connect it back with what we did yesterday to remember what we have to be between. Okay, so the inverse tangent of the tangent of x will equal x. Okay, inverse tangent, regular tangent, cancel out. But what angles did we have to be between for tangent?
Negative 90 to 90.
Negative 90 to 90, can we include them?
No.
No. So this time I don't have the equal to's. Okay, negative 90 to 90 or negative pi over 2 to pi over 2. Right. Now, this last one's a little different. It's different than any of the other ones we did. Okay, did I show you guys the graph of tangent yesterday? So we looked at that. It looked really different. Does anybody remember how high the graph went? Forever, infinity. And how low did it go? Yeah. And if it goes down forever, what would that be? Yeah, it's negative infinity. Okay, so this graph goes up forever and it goes down forever. So what that means is this formula always works. It's impossible to come up with an example that doesn't work. Right, and we'll try one example with the tangent. Right. So Ashley, looking at this one, is it formula 6a or 6b? 6b. So is that going to work? Yeah. Okay. Whenever it's 6b, you don't even have to think about if it works. It always works. As long as you have a number there, any number will work. Okay, so any questions on these 6 formulas if I put one on the test, either as like a yes, no, or a simplify? All right. So the last thing we're going to look at for this week is section 4.1, and we'll split it over 2 days. Okay. Section 4.1 is on right triangle trigonometry. Okay. Kind of the big picture goal here in right triangle trig is in a triangle, there's 3 sides and there's 3 angles. We need to find them all. Okay, that's basically what we need to do. You'll be given some information to start with. Okay, out of those 6 things, 3 sides and 3 angles, I have to give you a couple things to work with. Okay, and because we're working with right triangles, that also means something else. Okay, so we'll talk about that. So a right triangle, any triangle with a 90-degree angle. So in every problem we do this week, that's one thing you already know. You're going to have a 90. But in addition to that, I have to give you 2 other things. And one of them has to be a side. Okay. Does anybody remember in a right triangle what we call the 2 shorter sides? Oh, Bailey, do you remember that? The name of the 2 shorter sides in a right triangle?
I know the longer side.
Okay, what's the longer side?
Hypotenuse?
Yeah, it's good. Long side is the hypotenuse. Anybody remember the shorter sides? Yeah.
I don't know if it's the same in physics, but it's opposite and adjacent.
All right, those are going to be the names that we're going to use for them, opposite and adjacent, but they're both called something. You have 2 of them. It's not your arms. They're your legs. Okay. The 2 shorter sides in a triangle are the legs. Sometimes one will be opposite, one will be adjacent. We'll talk about that in a little bit. Okay, what's an acute angle? Yeah.
Angle less than 90.
Okay, it's less than 90. And one more thing we have to say. We have to narrow it down a little bit, just more than saying less than 90. What else does it have to be? Negative 10 is not an acute angle. But negative 10 is less than 90. So what else do you think we have to say?
Larger than 0.
Yeah, it has to be larger than 0. Of course, if we're solving problems about angles in a triangle, you'd never have a negative angle anyway. Okay, but that's the definition of an acute angle. Less than 90, more than 0. All right, so next thing I want to take a look at is the Pythagorean Theorem. Okay, the proof of where the theorem comes from, it's actually pretty easy to do just by drawing a picture. Okay, you don't even really need to do a lot of work. You can draw a picture, and it pretty much explains the Pythagorean Theorem. We're not going to go through that right now. But I want to know, what is the Pythagorean Theorem? Yep.
Like the actual theorem.
Sure. Yeah.
Okay,
Okay, so a squared plus b squared equals c squared. That's often how we represent the theorem. Now, can you explain what these a, b's, and c's are? Because I don't have those on the board anywhere yet.
The first leg on the left, that would be A,
Hmm?
like on the triangle. The second leg on the bottom would be the hypotenuse is ABC.
Yeah. So the important idea with the Pythagorean theorem is to understand you take one leg and square it, you take the other leg and square it, you add those together, and that's equal to the hypotenuse squared. You can call the sides A, B, and C, X, Y, and Z, whatever you want to call them. Well, Larry, Curly, doesn't really matter. But just make sure that you square one leg, square the other leg, add them up, it equals the hypotenuse squared. Okay, another fact that I might have written in a little bit, but it's important about the angles. Does anybody know any fact about all the angles in a triangle? Yep, they add up to 180. All right, so that's a fact we can use to help us out. All right, so in a minute, we're going to define the 6 trig functions. Okay, we already have defined them once in this class. We did it last week with a unit circle. Okay, we had like sine was y, cosine was x, tangent was y over x. Well, now we're going to define them one more time, but we're going to use the words opposite, adjacent, and hypotenuse. Okay, hypotenuse is pretty easy to define. Okay, the hypotenuse is always where in a triangle? Yep, it's the longer side, and it's always across from the right angle. Okay, opposite and adjacent are a little bit more vague. Okay, the answer is where are these? It depends. Yep, it depends on where you put the angle. Okay, it's kind of like saying, well, where's left and where's right? Well, it depends which way you're facing. Okay, if you're facing me, right would be towards the door and left would be towards the window. Okay, but for me facing you, that's reversed. Left is the door, right is the window. All right, so opposite and adjacent are what we call relative terms. Okay, it depends on where you put the angle. So if I put the angle in the bottom, opposite is the side that does not form the angle. It's the side that's farthest away. In other words, if I took this side away, I'd still have an angle right there. Okay? So it's the side in the triangle that doesn't form the angle that we're talking about. It's the farthest away, opposite. Okay, and then adjacent is the side in the triangle that does form the angle. Okay, and if you took that side away, you wouldn't have an angle anymore. So in this picture, this side is adjacent. It's adjacent because it's right next to the angle. If I took it away, I'd no longer have an angle here anymore. Okay, so the adjacent side is one of the sides of the angle that we're referencing. And it's not the hypotenuse. Okay, so that's how you'd label that diagram. All right, let's suppose we put theta here. Okay, Melissa, where would my opposite side be now? Yep, now opposite is the bottom. And Carter, what about my adjacent side? Yeah, the side on the left, it's the height. And did changing theta change where the hypotenuse is? No. Okay, so the hypotenuse is always in the same spot. Okay, it's kind of like in this room saying what direction is up. It doesn't matter if you face the wall, if you face the door, if you face the window, up is always the same way. Okay, but left and right change depending on which way you face just like opposite and adjacent change depending on where you put theta. Okay, so they're, again, what we call relative terms. All right, so any questions on opposite and adjacent? All right, so now that we have those two terms with hypotenuse, we can write the definitions of our 6 trig functions, just like we did last week. But now we're not using x's and y's, we're using opposite and adjacent. Does anybody know the definition of sine? Using the terms opposite, adjacent, and hypotenuse?
Opposite, hypotenuse.
Opposite over hypotenuse. Good. Okay, how about cosine?
Adjacent, hypotenuse.
Yep, adjacent over hypotenuse. And lastly, the tangent is opposite over adjacent. Right. Now, the other 3 trig functions we don't use as much. Okay? The reason we use these 3 a lot is because we have buttons on the calculator for them. Sine, cosine, tangent. Anybody give me the names of the other 3 trig functions? Yep.
Cosecant.
Yep, the cosecant.
And then I don't know how to say the second one, but it's SEC.
The secant.
Secant.
Yep.
And then the COT.
Cotangent. Yep. So we have the secant, the cosecant, the secant, and the cotangent. Now, does anybody remember from unit circle trig what we did with the 3 on the left to get the 3 on the right? We just flip them. Okay, so your cosecant is going to be what? Yep, hypotenuse over opposite. Your secant is hypotenuse over adjacent. And your cotangent, adjacent over opposite. And this really is exactly the same thing we did last week. When we did it with x's and y's, this is the same thing. Just a different way of looking at the picture. Does everybody have those six definitions? Okay, really, if you're trying to memorize them, you only need the 3 on the left. And then the 3 on the right are just flipped. Okay, and there is a way to try to remember the 3 on the left. Does anybody know? Yeah? Sakatoa, good. I've had some people say Sacagawea before. It's not Sacagawea, but I'm not sure that's going to help you. But Sakatoa will help. Can you tell me, Steve, what does that mean? What's that stand for?
Sine. Opposite, hypotenuse.
Sine is opposite
Hypotenuse.
over hypotenuse.
Cosine. Adjacent, hypotenuse.
Cosine is adjacent.
And then
Hypotenuse?
tangent, opposite.
Tangent is opposite over adjacent. All right, so there's a way you can remember it, just kind of reading, reading down, reading vertical. Don't read across, that doesn't make much sense. It'd be odd art or something, I don't know. That's not going to help you. All right, so just read down. All right, so what we'll do is just practice finding the 6 trig functions of theta. Now, for today, we're not actually finding theta. Okay, we're never going to know the size of this angle today. And you might say, well, how can you describe all these things about the angle and you never even know how big the angle is? Hey, the example I usually give is it's like if you meet someone on the street and you describe a bunch of things about them without knowing the person's name. Okay, you can just look at somebody without knowing their name and describe their eye color, hair color, how tall they are. But you don't need to know the person's name to do any of that. Okay? Well, we're describing the sine, the cosine, the tangent, all that stuff. But we don't need to know the angle's name. Or normally we call it the size of the angle. Okay, but before I can even start to describe these things, what am I missing in this triangle? I'm missing the hypotenuse. And I need that for 4 of the trig functions. Okay, so how can I find the hypotenuse in this triangle? Yeah.
Can you use the opposite over
You don't need anything I taught you today. Something that you learned back in geometry. More basic than trigonometry. Yeah. The Pythagorean Theorem. Right? You know 2 sides. We can find the third side. So if you want to call the third side C, 3 squared plus 4 squared equals C squared. Okay, Nick, what's 3 squared?
9.
Yep. And 4 squared? Good. 16. If we add those up, we get 25. So what is my hypotenuse here? 5. Okay, now I can go through and find my trig functions. Okay, how about Sydney? What would my sine be? 1 more time?
4 over 5.
Good. Opposite over hypotenuse? 4 over 5. Okay, Bailey, how about my cosine?
3 over 5.
3 over 5. And Emily, my tangent? Right. What's our definition for tangent again? What 2 sides do we need? Opposite over adjacent. So what side is farthest away from theta? The 4. And what side is right next to it? That's not the hypotenuse. 3. Okay, so there's our tangent, 4/3. Okay, Ashley, how about my cosecant?
5 over 4.
Yep, just flip it, 5 over 4. Okay, Hunter, how about my secant? 5 over 3. And how about Alyssa? What's my cotangent?
3 over 4.
3 over 4. Okay, and those are the 6 trig functions. Now on the test, for some reason, people get this confused with finding the angle. Okay, we didn't find the angle. All we did was find trig functions of the angle. And that's all you have to do. Okay, tomorrow, we'll take one of these 6 and we'll actually somehow cancel out sine. Okay, think about what cancels sine. We did that earlier today. And we'll get theta by itself. Okay, we'll do that tomorrow. Okay, questions on that? All right, so complementary angle theorem, that'll be the last thing we look at. Okay, but to build up to that, we got to just make sure we understand what complementary angles are first. Okay, does anybody remember from geometry what complementary angles are? Yeah, Amy? Those are 2 angles that add up to 90. Okay, and specifically it's 2 acute angles. So you can't have like -10 and 100. Even though that adds up to 90, those are not complementary. Okay, we're talking 2 positive angles that add up to 90. Okay, so my next statement says that if you look at the 2 acute angles, okay, not the 90, but the 2 acute angles in a right triangle, they are always complementary. Why? Why would the 2 acute angles in a right triangle always have to be complementary?
Because Triangle adds up to 180.
Okay, all the angles in a triangle add up to 180. Yeah.
And you always have a right angle?
And we always have a right angle in a right triangle, which is how much?
90.
90. So if they all have to add up to 180, and we've already used up 90, what's left?
90.
We have 90 degrees left for the other two angles. They have to add up to 90. Okay? That's why the two acute angles are always complementary. All right, so any questions on the idea of complementary? All right, so this is the first half of the complementary angle theorem, understanding what complementary means. The second half is understanding what cofunctions mean. Right, so up until now, we've paired our trig functions like this. Sine with cosecant, cosine with secant, tangent with cotangent. We've paired them up as reciprocals, which means you flip one to get the other. Okay, well now we're going to pair them up as cofunctions. Okay, and there's three pairs of cofunctions. Okay, the first one is sine. And does anybody have a guess what the cofunction of sine would be? That's going to be the cofunction for something else. Cosine. Basically, if you put the word co in front of sine, you get cosine. So sine and cosine are cofunctions. How about secant? Cosecant. Put the word co in front of it, and it becomes cosecant. How about tangent? Cotangent. This one happens to be the same as what we've been doing all along. Tangent and cotangent are cofunctions, and they are reciprocals. You flip one to get the other. Okay, so these are your three pairs of cofunctions. All right, so what I'm going to do is I'm going to look at this triangle, and I'm going to write down some of my trig functions. Okay, let's start with the sine of alpha. Now it's not going to be numbers this time. It's just going to be letters. Okay, so sine is opposite over hypotenuse. All right, so Steve, what would the sine of alpha be here? What's opposite alpha?
A over B.
Perfect. A over, what's the hypotenuse?
Oh, C.
C. Okay, any question on that? What's the sine of alpha? So sine is opposite over hypotenuse. And that's it. Okay, so now I want to find something different. I want to find the cosine. And this time I don't want to use alpha. I'm going to use a different angle. I'm going to use beta. Okay, I want to find the cosine of beta. So cosine is adjacent over hypotenuse. John, what side is adjacent to beta? A. And what's the hypotenuse?
C.
C. So what do you notice if you compare the sine of alpha to the cosine of beta? They're the same thing. Okay, we'll try one more of those. Let's do the tangent of alpha. All right, so Carter, what's tangent again?
Tangent, opposite over adjacent.
Yep, opposite over adjacent. And what's opposite alpha here?
Opposite alpha.
So what side is opposite alpha? B is next to it.
Oh, A.
A, yeah. A is opposite. And the side that's next to it or adjacent?
Yeah,
That's B. Okay, so the tangent of alpha is A over B. Now I'm going to do something different. I'm going to find the cotangent. And I'm not going to use alpha. I'm going to use beta. So cotangent is adjacent over opposite. Okay, Amy, what side is adjacent to beta? A. And what side is opposite? B. Notice again, those two things came out the same. What's the relationship between sine and cosine? They are what again? Same relationship as tangent and cotangent. They're what? They're cofunctions. And what's the relationship between alpha and beta? What kind of angles are they? They're complementary. Complementary. Right? So the complementary angle theorem is based on two things. One, having cofunctions. Two, having complementary angles. And that's the whole theorem. It says what we just kind of showed. If you have cofunctions and you have complementary angles, they come out the same. Cofunctions of complementary angles are equal. Okay, so we'll look at a few examples, and then that'll be it. Right, so using the complementary angle theorem, I want to fill in what goes on the right here. So I have to think of two things. I have to look at what's on the left, and the first thing I have to do is look at the function, and in my head, figure out what's the cofunction. Okay? After I figure that out, I have to look at the angle, and then ask myself, what's the complement of that angle? What do I add to it to get 90? Okay? So let's start with the cofunction. What's the cofunction of sine? Cosine. And what's the complement of 30? 60. Right. So if you took, on your calculator, if you took the sine of 30, okay, or you do cosine 60, you get exactly the same thing. Now, this theorem doesn't tell you that the value is 0.5. All it tells you is whatever the value is with what's on the left, it's the same as what's on the right. Okay. How about the next one? Tangent of 15. Anybody think they know what goes on the right? Okay, 75 is the complement, so that's part of it. And what's going to be my trig function? Cotangent. Okay, I'm not going to type it in, but if you want, you could check it on your calculator. The tangent of 15 is the same as the cotangent of 75. I have no idea what the tangent of 15 is. I don't know. But I know it's the same as cotangent 75. Okay, and how about the last one? Secant of 40. Cosecant of 50. Yeah, they're the same thing. Again, I don't know what the number is. I don't know the value of this. But these two things are the same. And I'll show you where that can help us in our last problem. Okay, I want to find the sine of 15 divided by cosine 75. Now, like we did up above, let's do the same thing for sine of 15. What is sine of 15 the same as? What's the
Cosine of 75.
the cosine of 75? Okay, look what's in the bottom of that fraction. Okay. You have angles that are complementary. Okay, they add to 90. And you have cofunctions. So the sine of 15 is the same as the cosine of 75. So when you divide them, what would you get? 1. Okay, I have no idea what the sine of 15 is. I have no idea what the cosine of 75 is. But I know they're the same. And if you divide two things that are the same, you get 1. Okay. Now, what if they stuck a negative in front? Now the answer would be, just stick a negative in front, a -1. Okay, any question on that one? Okay, so it's a very special problem for it to work out like this. The angles have to add to 90, and these have to be cofunctions. If it was sine of 16 divided by cosine 75, I can't do it. Okay, I need a calculator. Okay, let's look at this one. Tangent of 12 minus cotangent 78. Okay, what do you notice about tangent and cotangent? Yep, they're cofunctions. What do you notice about 12 and 78? They add up to 90. So you have cofunctions of complementary angles. Means they're equal. Okay. So what would we get if we subtract these two things? Yeah, we get 0. Again, we don't know what the tangent of 12 is. We don't know the cotangent of 78. But using our theorem, we know they're the same. Right? So again, check for cofunctions. Check for angles that are complements. Right? So this trick will work with division. It'll work with subtraction. How about addition? If you add two things that are the same, do you always get the same answer? No. You get the thing doubled. All right? So when you add two things that are the same, I can't tell you what it always would come out to. So you'll never see this trick with addition. You won't see it with multiplication either. If you multiply two things that are the same, you don't always get the same answer. You get that thing squared. Okay, so any question on how to use the complementary angle theorem? All right. All right, so the homework, it's in two parts. Okay, the first part is all yes or no questions, like the first few examples we did. Okay, that's 187, 46 to 51, 53 to 55 all. And then the last part is on page 255, and this is on the stuff with right triangles, okay, Sakatella stuff. And it's 9 to 21 odd. Okay, you've got about 15 minutes. Okay, so please get started. If you need any books, there's some up on the counter. And if you need help from me, I will walk around and help you out.